Okay, so we've been looking at implicit differentiation. No, we've been looking at the chain rule. So now I want to do a problem. Okay, so the upper radius of the frustum of a cone is 10 inches. The lower radius is 12 inches. And the height is 18 inches. At what rate is the volume changing if the upper radius decreases at a rate of 2 inches per minute? The lower radius increases at a rate of 3 inches per minute, and the height decreases at a rate of 4 inches per minute. Okay, so let me explain this problem. So we have the frustum of a cone. So the frustum of a cone is as if you took a cone and you chopped it off. So the upper radius is 10 inches and the lower radius is 12 inches. Okay, so if I were going to draw that frustum of a cone, I would have something that looks like this. So I would have here, and then I would down here have something like this. And then I would connect them. Okay, so as you can see, this is the frustum of a cone. All right, my line is not really in a good place. Okay, so can you see the frustum of the cone now?
Yes.
Good. That's what I need. Okay, so here's the height. Okay, so the volume of a cone, or the volume of the frustum of a cone, is as follows. So the volume is equal to 1/3 pi z times x squared plus xy plus y squared, where x is the upper radius, y is equal to the lower radius, and z is the height. Now, this is a rate of change problem. Okay. So a rate of change problem implies they want dV dt. So how is the volume changing with respect to time? Okay. Now, they told us that volume, so we know that the volume is a function of x, the upper radius, y, the lower radius, and z, the height. And each one of these is a function of time. So I can use the chain rule to say V to get dV dt is going to be the partial of V with respect to X times dx dt plus the partial of V with respect to Y dy dt plus the partial of V with respect to Z dz dt. Okay, so do you understand that?
So this is the chain rule, or?
This is the chain rule. So notice that V, after everything is all said and done, if I added all the X in and the Y in and the Z in with the function of T, V ultimately at the end is a function of T.
Okay.
So I can find dV dt by going out each path. So I got to go out here, then I have to go out here, and then I have to go out here. So I have to go out each path in order to get dV dt.
Okay.
Okay, that's what we're doing. Okay, so now we need to find these partials. Okay, so my V is up here. I need to move it. Okay, so here's V. So I'm just going to move it down here just so I have it. Okay. So now I need to find the partial of V with respect to X. All right, so what's the partial of V with respect to X?
Two-thirds pi z x. No.
Okay. Well, both of these terms, this is how I would do it. Both of these terms have an X, right?
Mm-hmm.
Okay, so therefore each one is going to have 1/3 pi z as a coefficient. So then I would get 2x
So you just leave it plus
with
1.
y, because that's the coefficient, yeah.
Okay.
And then when I do partial of V with respect to y, I would keep the 1/3 pi z, right?
Yeah,
And
plus
then
x and then 2y.
good. And then the partial of V with respect to z,
Um, 1/3 pi. And then you multiply by the thing in the middle.
the x squared plus xy.
Mm-hmm.
Okay, good.
Yes.
Okay,
Wait,
now,
why change it z squared?
because that's a mistake.
Oh.
Okay. All right, so now we need to go back. So we got everything we need. Now we need to go back to the problem, okay? So this is happening when, notice we didn't put any numbers in yet. Now we can put the numbers in. This is happening when the upper radius, which is x, is equal to 10. So now they tell us x is equal to 10. The lower radius y, I believe, was equal to 12. And then the height z is equal to 18, right?
Mhm.
And then they say at what rate? Okay, so now they say the upper radius is decreasing at a rate of 2 inches per minute. What are they giving you?
You said, say it again.
The upper radius decreases at a rate of 2 inches per minute. What did they just give you?
The slope. Oh, no, that's X. They gave you X. Isn't that X?
They tell you how x is changing.
Yeah.
So what is that?
Dx dt.
Good. And it's decreasing at a rate of 2 inches per minute. So what do I write here?
What'd you say?
It's decreasing at a rate
-2.
-2. dy dt.
Can you go back to the problems? I'm trying to get out. It's 3
And dz dt.
is -4.
Good. Okay, so now let's find the partial of v with respect to x. Okay.
Okay. You said the partial of v with respect to x.
So partial of v with respect to x is 1/3 pi. Z is 18 times 2 times x, which is 20 plus 12. So that's 6 pi times 32.
Mm-hmm. 192 pi. I think. Oh, 260. Wait, 32 times 6. Yeah, 192.
Yeah, that's right. 36 times 6 is.
Yeah, I did put that in my calculator by
Okay.
accident, but I had the 32 times 6 in my head. That's why I had to check.
Okay. Partial of v with respect to y is 1/3 z, 1/3 pi z, which is 18 again, x, which is 10, plus 2 times y is 24. So that's 6 pi times 34. So we just add on another 12.
204, yeah.
Yeah. And then the partial of v with respect to z is 1/3
Pi,
pi
100 plus 120 plus 144. So that's 364.
That doesn't go evenly?
No.
Okay, it doesn't. It's 364. Wait a minute, 100
3.
plus 120 plus 144. And that was 364.
Uh-huh.
Okay, so therefore we get dv dt turns out to be 192 pi times, oh, there it is, -2 plus 204 pi times 3 minus or plus 364 pi over 3 times -4. Would have been nice had they made that divisible by 3, but whatever. So it turns out to be minus 772 over 3 pi. So the volume is decreasing at that time. So the volume, and this is cubic inches cubed per minute. Okay. We good?
Mhm.
Okay. All right. The last thing is the implicit differentiation. Okay. So sometimes it's not giving to you where it's easy to find the derivatives of z. So we have the implicit. So generally, we've been able to, so up to now, we've had z is equal to f of xy. We were able to find the partial of f. We could find f sub x, f sub y, f sub xy. We could do all that, right? Okay, well, now what happens if you have a function now that is, it's not written nicely that you can take derivatives. So now we want to do implicit differentiation. Okay. So for implicit differentiation, we want to suppose that we have w is a function of x and y. All right. And here where y is a function of x. Okay, so we have something that looks like this. So you have w is a function of x, and it's also a function of y, which is also a function of x. Okay, so we can rewrite it as we're given some big function f of x and y is equal to 0. Okay, so we're going to use the implicit function theorem. So we're going to take the partial with respect to x. So we get 0 is equal to the partial of w with respect to x is equal to the partial of f with respect to x plus the partial of f with respect to y, derivative of y with respect to x. So now I can solve for dy dx. So dy dx simply becomes minus the partial of f with respect to x over the partial of f with respect to y. Now we've done that before. So here's an example. We've done this before. So example, we have e to the x over y plus the log of y over x plus 15 is equal to 0. So now notice I can't write y as a function of x. So dy dx says take the derivative of f or the partial of f with respect to x and then divide by the partial of f with respect to y. Okay, so here f of xy is the e to the x over y plus the natural log of y over x. So if I want to find dy dx, I got to find how f depends with the partial of f with respect to x. So the partial of f with respect to x. So I need to take the derivative of this with respect to x. Well, the 1 over y is just a constant. So I get 1 over y e to the x over y plus, then when I take the partial with respect to x here, I get the log, I get y over x in the denominator, and the derivative of y over x, which is minus y over x squared. So that's what I get. And then I do the partial of f with respect to y. So the derivative of that is going to be minus 1 over y squared times e to the x over y plus, I'm going to put the log, put y over x in the denominator. And then the derivative with respect to y is just 1 over x. Okay, so that's the cray thing I get. All right.
Oops.
So therefore, dy dx going to equal minus 1 over y e to the x over y minus, when I multiply by x over y, I just get, wait a minute, which will, oh, I'm doing it wrong. The partial with respect to, no. The partial with respect to x goes on top. So I get x over y. So this should just give me minus 1 over x. And then the denominator, I get minus 1 over y squared. It's missing an x. E to the x over y. And then when I flip that, that just gives me 1 over y. And there really is no way to make this nice. I can multiply by y squared x, but that's what it is. I mean, I can multiply everything by y squared x, and I would get, are they both negative? Are both of these negative? Nope, this one is not negative. Okay, Ray, say something is wrong. That's not negative. It doesn't matter, that's the answer. If I can multiply by xy squared, but that's the answer. Okay. All right, so that's if you only have a function of 2 variables, right? So w is a function of x and w is a function of y, which is a function of x. So in order to find dy dx out of here, you can get the derivative of y with respect to x. You have to divide the partial of f with respect to x divided by the partial of f with respect to y. Okay, now what happens when you have a bigger tree? Wait a minute, I think that's all I have. Nope, that's it. Nope, that's it. That's it. There's no more. Oh, wait a minute. I think I do have an example. Let me look to see how much they cover real quick. Because if they don't cover all that cray-cray stuff, I'm going to not do it. But I will do it if the book does it. So when I get down to here, it does dy dx. Oh no, it does do all the rest of it. Okay, so it does it, but it doesn't derive it. The derivation is makes it more difficult. So I'm just going to give it to you. Okay. All right, that's what you do in that case. Now, okay, so lastly, suppose you have f of x, y, and z such that z is a function of x, y. Okay. Then, in order to get the partial of z with respect to x, you have to take the partial of, and this is negative, the partial of f with respect to z, with respect to x, and then divide by the partial of f with respect to z, and then the partial of z with respect to y is negative the partial of f with respect to y, and then you have to divide by the partial of f with respect to z. Okay, so what in the world does that mean? Okay, so suppose we have example x squared plus y squared plus z squared is 4. So that's a sphere of radius 2. Okay. In order to find the partial of z with respect to x, you've noticed now that we're assuming z is a function of x and y. Okay. But notice if I wanted to solve for z, I could, but solving for z is a pain. So I just need to find the partial of f with respect to x. That's 2x. The partial of f with respect to y. That's 2y. And the partial of f with respect to z. That's 2z. So therefore, the partial of z with respect to x is minus 2x over 2z. So that's minus x over z without having to do the whole nasty problem. And then the partial of z with respect to y is negative 2y over 2z. So that's minus y over z. And you're done. Okay. So here's one example. X e to the y z squared is equal to 10. Now, I could solve for z, but solving for z would be, wow, let's see. I won't even make it z squared. I'm just gonna make it plain old z. Find, assuming z is a function of x and y. Find z sub x and z sub y. Now, I could solve for z. So one way I could do it would be get e to the yz is equal to 10 over x, and then take the log of e to the yz is equal to the log of 10 over x, and then have yz is equal to the log of 10 over x, and then divide that by y to get z. And so now I could find z sub x and z sub y. Or I could have done, the second way I could have done it is looked at the problem and said, what is the partial of f with respect to x? So now I'm going to rewrite f of x, y, z as x e to the yz minus 10. Okay. So the partial with respect to x is simply e to the yz. The partial of f with respect to y is xz e to the yz. No, xy. Yeah, partial with respect to y. So e to the yz, a z is going to come down. Yep. And then the partial of f with respect to z would be xy e to the yz. So therefore, the partial of z with respect to x is minus e to the yz divided by xy e to the yz, which is minus 1 over xy. And then the partial of z with respect to y would be minus xy e to the yz over xz e to the yz. So that's minus y over z. And I'm done. Okay. And actually, y over z, I know what z is. I can put z in. Oh, no, I don't. I would just leave it like that. That's it. Okay. So that's it on partial derivatives. They are wonderful, fun, and now we are getting ready to use them for something else.